Walk up to a cafe counter and you have two ways to order. You could recite the recipe, grind the beans, pull a shot, steam the milk, pour. Or you could just describe what you want. One strong cappuccino, please. Both get you the same cup. Databases have exactly the same two styles. Relational algebra, which we met earlier, is the recipe, a chain of operators that says how to compute the answer step by step. Relational calculus is the description. It says only what the answer tuples must look like. The set of rows whose name we want, where the student is older than 20, and lets the system find them. This declarative style is the one SQL grew out of same result, different thinking. Here is the whole shape of tuple relational calculus in one line. The set of all tuples T for which the predicate P of T is true. Two pieces do all the work. The T on the left is a tuple variable, a single row that roams over a table. And P of T is a logical condition, and every row that makes it true joins the result. That predicate draws on a small vocabulary. Membership like T belongs to student, dot notation like T dot age for one attribute, the connectives, and, or, not, and the usual comparisons. Let's put it to work. Let's make it real. Here's a student table and a query in that form. The set of tuples T where T is in student and T dot age is greater than 20. To evaluate it, we just try every row as T. Amit is 19, not above 20, so no. Bina is 22. Yes, she qualifies. Chirag is exactly 20, and 20 is not greater than 20, so he's out. Divya is 23. Yes. So the result holds to hold tuples, Bina and Divya. Notice we never told the system to scan rows. We only described the rows we wanted, and the answer fell out. A condition on one row only takes us so far. The real power comes from quantifiers, and the first is there exists, a back-to-front E. There exists E, such that something is true. Here's a question that needs it. Which students are enrolled in something? Anything at all? On the left, the students. On the right, an enroll table listing who takes which course. In calculus, we write it like this. The set of students T for whom there exists an enroll row E, whose SID equals T's, at least one enrollment row points back at this student. Now existential search goes to work, student by student, hunting for one matching enroll row. Amit, SID 1, several rows point at him, and one is enough. He's in. Chirag and Divya each have a row 2, both in, but Bina, SID 2, scan the whole enroll table, and not a single row mentions her. There exists no matching E, so Bina fails the condition. She's the one student left out. The answer, Amit, Chirag, and Divya. That's the essence of there exists. It asks for just one witness. Find a single row that works, and the condition is satisfied. The second quantifier is the demanding one, for all, an upside-down A, where there exists is happy with a single success. For all insists that every case holds, no exception. It's the hard one. The calculus cousin of division in algebra. Here's the question that forces it. Which students are enrolled in all of the CS department's courses? We need 3 tables now: students, courses, and enrollments. The CS courses are 101 and 102. In calculus, it reads like this. The set of students S such that, for every course C, if C is a C's course, then there exists an enrollment of S in it. That if then inside of for all is the classic shape for all of a kind. Read that implication carefully. It doesn't demand every course in the catalog, only that if a course is C's, the student is in it. Non-CS courses make the if part false, so they're automatically satisfied and simply don't matter. So check each student against both CS courses. Amit has 101 and 102. Both covered, he qualifies. Bina is enrolled in nothing, Missing both. Out. Chirag has both CS courses. In. But Divya, watch closely. She took 101 only. 102 is missing. And for all tolerates no gap. So Divya is excluded. Answer. Amit and Chirag. And here's the lesson that makes quantifiers click. Divya was enrolled in something. She'd pass a there exists test easily. But she's not enrolled in everything. So she fails for all. Some is not all. One idea underpins reading any calculus formula cleanly. Which variables are free and which are bound? Take this query. The names of students enrolled in something. The variable t appears before the bar. So it's the output. We call it free. It isn't tied to any quantifier and its values become your answer. The variable e is introduced by there exists. It's bound. It lives only inside that quantifier's parentheses, witnesses a match, and never leaves. So the rule is simple. The free variable is what you return. The bound ones are private helpers. And always keep their names distinct. Tuple calculus has a close sibling, domain relational calculus. Almost the same idea, but the variables range over something different. Instead of standing for a whole row, each variable stands for a single domain value, one column's worth. Put the two side by side on the very same query, students older than 20. On the left, tuple calculus, t is one row, and we write t.age. On the right, domain calculus, the angle bracket triple I, n, names the three columns, ID, name, age, as separate variables, and the condition is just a greater than 20. Same answer, Bina and Divya. The two differ only in whether a variable is a row or a value. Domain calculus is the one that inspired the fill-in doubling style of query by example. Logic hands us enormous freedom and one sharp trap with it. Look at this innocent-seeming query. The set of tuples T that are not in student. Just a not in front of a membership test. Ask what it actually returns. Every tuple that is not a student. That includes every possible row of every other shape and value in the universe. An endless, infinite set. A query that never finishes and never fits in a database. The cure is a rule called safety. A safe expression only returns values that already live in the database. In practice, tie every variable to a real relation and use not only to filter within that finite set, never on its own. Every practical query and every SQL query is safe by construction. Now the punchline of the whole chapter. Let's write one query both ways. The names of students enrolled in CS 101. In algebra, it's a recipe. Select the CS 101 enrollments, join to student, project the name. In calculus, it's a description. The name of any student for whom there exists a matching enrollment in CS 101, joined by SID. Different words entirely, and yet both return exactly the same table. Amit, Chirag, and Divya. That is no coincidence. It's a landmark result. Chord's theorem. Relational algebra and safe relational calculus have exactly the same expressive power. Anything you can write as a recipe, you can write as a description. So neither is more powerful. Algebra tells the machine how, calculus tells it what, and both are the bedrock under every relational database. Your turn. Here's an EMP table and a tuple calculus query. The set of tuples T in EMP where T.salary is greater than 50,000. Pause now and work out the exact result. Watch the boundary carefully. I'll wait. Let's check each row as T. Ravi earns 45,000. Below the line. So no. Sarah earns 60,000. Above. Yes. John earns exactly 50,000. And 50,000 is not greater than 50,000. So John is out. Meera, 72,000. Yes. So the answer is two tuples, Sarah and Meera. If you kept John, you were caught by the strict greater than. It excludes an exact match. Get that. and you're reading tuple calculus correctly. Trap 1. Reading a calculus query like a program. There's no first do this, then that. It's a single logical statement. And the order you write, conditions changes nothing. Trap 2, the deepest. Confusing there exists with for all. Some is not every. In a CS course needs there exists. In all CS courses needs for all. Mix them up and the answer is wrong. Trap 3. An unguarded knot. The set of tuples not in a relation is infinite and meaningless. Anchor every variable to a real table first, then filter. Trap 4. Muddling the two calculi. In tuple calculus, a variable is a whole row, t.age. In domain calculus, it's a single column value. Same logic, different grain. And trap 5. Tangling free and bound variables. The one before the bar is free, your output. The ones a quantifier introduces are bound and private. Never reuse a name across the two. Let's lock it in. Relational calculus describes the answer rather than computing it. The set of tuples T satisfying a predicate P. Its power is the quantifiers. There exists means some, one witness is enough. For all means every, no exceptions. And the variable before the bar is free. Your output, quantified ones, stay bound inside. Keep every expression safe, so its result is finite. And remember Chord's theorem, safe calculus and relational algebra are equal in power. One says what? The other says how. Master this, and you can describe any query in pure logic.